What we'll do is we'll go through the challenges of designing for cloud scale. And when I say cloud scale, I'm referring to a scale of, call it north of 1 million servers. Uh, what kind of hardware designs would need to be done to accommodate the variety of services that are hosted in the cloud? And what is the nature of the workloads? So we'll go through two examples to show you kind of how cloud workloads are so different from classic workloads. And then we will take a look at the actual server design that we use in Microsoft for hosting most of our big cloud services. And then we'll wrap up with the tools that we use to manage these servers. And so these are all, in production data centers, the tools that we use. So we'll go through that as well. So let's get started. Yeah, my name is Kushagra. I run the hardware engineering team at Microsoft, which is across the lake here. And basically, what me and my team do is we design server hardware with the intent of customizing it for our data centers. So this is not hardware that we go sell or anything like that. It's only meant for internal use for our cloud services. So just to take a quick look, just to kind of level set the conversation, if you look at the types of, the variety of applications that are hosted in the cloud, it varies from, applications that build on APIs that are presented, call it PaaS, call it, applications built on top of blobs or streams or other. There are VMs, you can do hosting and just bring your own workload. There are software as a service type applications where you just consume the service. There are, test and dev is usually done in the cloud these days. And, some people use it for backup and recovery. Some people use it for MapReduce type jobs just to do batch computing. Some people use it for HPC. And the point is that what's happening is, there is one place where all these workloads end up. And if you look at this range of workloads, they are very diverse. And we'll go into some more detail. To give you a sense of scale, this is kind of a slide that shows sort of the scale of some of the services that we run at Microsoft. So for example, for search, which is internet search, which is Bing, it's about 5.8 billion queries each month. Then there's a Skype and Office and Azure. So it's so the scale manifests itself in terms of network traffic, in terms of the compute resources needed, in terms of the storage capacity and the storage bandwidth needed. Eventually, that's what you have to take into consideration for designing. So some of the differences first. So before we go into the actual design points, let me just call out some of the principles for how it's different between, I took 3 design points here, and these are all order of magnitude different. So the first one is, a classic enterprise environment might be around, let's say, 10K servers. And the second one is, call it a hoster, maybe around 100K servers, so 10x more servers, but it's around 100K. And then you have, a cloud scale environment. So this could be, Microsoft or Google or Facebook or Amazon, the big first tier 1 cloud guys, right? Which is typically, call it north of 1 million servers. So in generally speaking, the differences you'll see when you operate at these different scale points is, on the design side. So first of all, the server SKU, or the actual server platform that you deploy, even though you have a variety of applications, you don't want to try to have one application per SKU. Because then what happens is you can never predict how many applications will be running in the cloud, and you end up with massive proliferation of these variety of servers, and you can't share servers between different workloads, which is kind of a waste of resources, and there is no fungibility. So you try to end up with a small set of SKUs. Maybe there's a compute SKU, maybe there's a storage SKU, maybe there's a heavy storage and light storage. There's a few number of SKUs. And then you try to map the application to the SKU versus the other way around. Right? On the redundancy model, in a classic enterprise environment, as you know, hardware is built to be extremely reliable. Typically there are multiple power supplies, there's multiple fans, there are RAID controllers so that you don't lose data. On the cloud side, it's completely orthogonal to that, right? Because the software is the one that's doing all the load balancing and the replication. So the hardware design, as a result of that, can deal with a lesser level of availability. So the numbers here I'm putting is like maybe it's about 2 nines. Electric utility, power from the utility is about somewhere between 2 nines and 3 nines. So if you can design it to be around that number, then you essentially are tied to the base things that you cannot control. The utility comes from somewhere else. The rest you have to deal with by doing balancing in software. So that's another design point to consider. So and as you think through this, right, think about, okay, so these are constraints, or rather, I would say it's the other way around, right? These are constraints that would have been there, but now you don't have them. How do you take advantage of these? On the designs, typically what you find is custom designs are the norm because nothing that exists in the public market, through suppliers, OEMs, they're pretty heavyweight and unnecessary features, so you end up designing it custom. And the final point here is, because you're designing it for a global, data center footprint, you have to take into account how all the different parts of the equation fit together. The big ones are the operating system, or the fabric that manages it across the globe. Then, of course, there's the data center. There is, of course, the server, and there's the network. So you think of it like a big distributed system, and what is the role of the server in that infrastructure? On the operations side, again, it's very different how you operate these servers. Break fix, which means, think about a hard drive going bad or a memory DIMM going bad, and you have to send somebody to replace it. In an enterprise environment, because your application is tied to a server, and if the server goes down, the application goes down, the operations personnel are typically 24/7. On the flip side, in the cloud, maybe you can wait for 2 weeks. In some cases, we don't send a technician to the server for maybe 1-2 weeks. And the reason that works is because that's not the only place where the data is stored. There is data replicated across multiple domains. So you can serve data from the other domains while this one is down. And that reduces the operational cost significantly, as you can imagine. How you find issues when they happen, you don't want humans to be in the loop because humans are slow and it takes a long time to go through logs, and so you end up deploying machine learning techniques in that case. So that gets you as far as pointing out where the issues might be, and then you can do the final level of debug yourself. For systems management, so these servers are distributed across the globe. You don't have any physical access. Systems management ends up being a simple thing like either turn it on and turn it off. In some cases here, the fabric that we have that runs the servers, if a server is exhibiting issues, first what we do is we try to reboot it without even knowing what the problem is, right? You try to automate the whole thing. You reboot it, you try it 3 times, and guess what? Most of the time it reboots and it comes back fine. Sometimes it doesn't. So then what you do is you try to reinstall the OS image, and you try that up to 3 times, and most of the times that works. So you do this kind of thing, and it's all automated, and most of the times, these sequence of tests works out, and you don't have to take any action, by sending somebody to the machine. But in case you have to, do it manually, then what you do is you just want to be able to turn it on and off. The domain for management is around 10,000 servers, so it's very different from enterprise. And when you replace the component that has failed, you don't replace a component, you replace a whole server. Because you don't want to waste time, for a technician to be sitting there and putting debug hooks or whatever. You send the technician, he pulls out the server, puts in a new one, takes the old one to the bench, and then you can run some diagnostics and find out what went wrong. So very different. And so that's the operational piece. Now let's take a look at what are the workloads. You can't. Sorry. Yeah, absolutely. Nothing leaves a data center unless it's secure erased. So that's a whole different. And I'll take questions after. So, okay. So when we talk about hardware design, you have to start with the workload. What is the workload you're trying to solve for? So let me take two workloads. These are big workloads. There's much more than that, but this will give you a good sample of what the workloads look like. And these are workloads that operate on hundreds of thousands of servers, right? So the first one is cloud storage. So if you have used Azure Blob Storage or Amazon S3, this kind of falls in that category. So how is that designed, right? So at least for the way we designed it was it's an append-only file system. So we're not using the traditional Windows file system. There is a custom file system that's designed, and it uses 3 GB chunks called extents. And every time you get a piece of data, you keep appending to that extent, and you use these as your basic building block. If you have to modify data, you read the extent, make the change, and do a read, modify, write back into the. So it's a very different way of doing file systems. And then there is replication that happens, so that you don't, if you happen to lose a drive or a machine or maybe even a rack, you don't end up losing all copies, right? So what happens there is, this is an example that shows how the data is replicated. Now, it's very inefficient to replicate it 3 times, because you end up with a 3x overhead for your data. So what we end up doing in this case is use erasure coding. There is a 14+4 encoding scheme that is used, which gives us about a 1.29x overhead. So think about that, right? You have only 30% overhead for getting data triple replicated. So there's a nice paper on this that was published, I think like last year in ASPLOS. So if you want to find out more details, you can go read that. But what happens as a result of this, so by doing this, you end up saving a lot of cost because you don't have to buy as many hard drives. But on the flip side, what happens is you put a lot of pressure on the network. So now your network has a lot of operations going back and forth, and every time you want to write something, you're doing multiple writes to different racks. You're doing garbage collection because you want to make sure that. So it's kind of like a JIT-like thing that happens, except it's happening at a larger scale. So very different workload. Let's take a look at a completely different workload, which is search. So here you're indexing the entire internet, and you want to respond. When somebody enters a query, you want to respond back to the user within call it 100 milliseconds. So you have call it maybe 50 billion documents in your store, and you want to return a result in 100 milliseconds. So it's a you can think of it like a database, but except it's not a classic database, right? So here you have rows and columns. The data is sharded across these. The rows provide the load balancing. The columns provide the the different pieces. And you do the lookups, and you get the first level of results, and then you start aggregating them, and now you have to rank them. Now, one thing I want to point out here, you see the big red dot in the middle that says neural net. So there is a ranking algorithm that will basically take the results that have come back and will determine how relevant are these results based on what a human would want to see. So it's a neural net that is trained all the time based on real-world queries and training sets. But it's very, very compute-intensive. And as a result of that, CPUs generally end up not doing such a good job at that kind of data set. So in Bing's case, we have experimented with FPGAs for that particular part of the code, and it has shown tremendous amount of gains. There was, again, a paper at ESCA this year, so if you want to find out more, you can find out about that. Again, the point here is that like the previous application you saw, the cloud storage, that was very network intensive, even though it's a storage application. In this case, it's a search application which should be latency sensitive, but it turns out it's also very compute intensive. So the point is, cloud workloads are very different. When you design hardware, you have to take this into account. There's several opportunities for doing offloading. So you have to make sure that while your servers are designed to be pretty homogeneous, you can also do specialization through offload accelerators and whatnot. In some cases, the data is read mostly write once a day. The Bing index is a classic example. You're just reading from the index all day long, and the index gets updated very, very infrequently. in some cases, we try to avoid random reads. You do sequential write streams, so the pattern of the workload on the disk is very different. And finally, for application, it's a whole different algorithm for application. There is no RAID. There is no duplication of data for durability. So they're very different. So again, coming back to what we're trying to do here is, what is the server infrastructure that you're going to design to take into account the variety of these workloads? So in addition to the nature of the workload itself, there are several other things to be considered. There's performance, there is power, there is cost, how fast your supply chain can operate, because that also gets, if the design is not optimized for supply chain, then you will end up having a long lead time to get the servers. Customization, so that you can do some special use cases. Simplicity for operations, because hardware breaks, and when it breaks, you have to figure out how to fix it. And uniformity, so that you can share these amongst a multiple set of services. In addition to that, so the first point is about the workload, which we talked about. The second thing is, these servers are deployed globally in data centers across different regions, US, Europe, Asia, South America, and whatnot, right? And there's different regulatory standards, safety standards, electrical standards. So you have to take that into account as well. So it becomes a pretty complex problem. You're trying to design one common server infrastructure, but then you've got to deal with this variety of workloads and data centers and electrical standards and whatnot, right? How do you go about doing that? So there are three principles that essentially matter in this case. The first one is, you got to make sure that the design is modular. Because if it's not modular, then you can't make changes to the parts that need to change. A good example is, you want to go from 10 gig to 40 gig, or you want to add a card for accelerating encryption or not, or you want to, have a way to, increase the flash capacity. It's got to be modular, so that's one key principle. The design has to be very simple, because as I mentioned before, most of the work is going to be done in software to deal with availability and redundancy, so the hardware can be really indeed very simple. So how do you strip all the unnecessary things out of hardware and leave it only to the main things that matter, which is compute, storage, and networking? How do you simplify the design? And finally, you have to design with an eye for operations. Eventually, this will go into data centers, and there'll be folks who are in the local region, in the data center, who are operating on these, and they need to, it needs to be pretty simple. Most of it is automated, but in case the automation doesn't work, you have to have simplicity there. So this is what we did. This was all contributed to Open Compute back in January, so it's all open source. It's the specifications for the servers. It's about 350 pages of technical specifications that's out there. The CAD models so that are out there. The source code for how to do systems management, so that you can do, all the operations part that I talked about. That's out there, and there's a link there if you want to. I'm going to post these slides so you can take a look. So you can go there and download the whole design if you want to. Some of the features of the design. So the three things, if you recall, I mentioned were modularity, simplicity, and operations. So one thing we did here for modularity was make sure that we end up sharing a lot of the common infrastructure components. So in this case, there's shared management. I'll talk more about the management piece given the focus of this specific conference. There's shared power. There's a shared signal backplane. And it allows for high density options. It allows for medium density depending on what your power envelope is and what you're configuring. If you end up doing GPUs, then you don't want to go high density as this one. This is a 12U design, so you see 24 servers in 12U. So this kind of high density works well for compute intensive workloads. And finally, it's optimized. The design is very simple. There's very little sheet metal in it. So it's optimized for contract manufacturing, which reduces cost in the end. On the chassis, so talking about simplicity, what we did was there are no cables in the design. There are absolutely no cables that come in the way of servicing. So think about, you see that visual there. If something were to fail, a hard drive failed or whatnot, all the technician has to do is, turn the latch, pull it out, and take it away. What we found, and that's the chart down there, is with cables, what happens is you get a lot of false errors. In some studies that we did, for network cables specifically, we found that it was reported that there's a network issue, and then you go and look at what the issue was, and it turns out that the cable was loose, or and all you do is you pull the thing out, you put it back, and it works fine. So it's just unnecessary overhead. It creates more operational cost, right? So we got rid of cables in this design, and that has helped a lot in making sure that we don't have to send technicians there when physical things start to break. Talking about reliability, hard drives are usually the ones that fail most often. The manufacturers will say that hard drive failure rates are 3%. In reality, they tend to be more like 6%. So then you start looking at, okay, how do I make sure that the mechanics of the hard drive are what they are? It's amazing that they even work, actually, if you think about it. The heads of the drives are over the platter by, it's like 2 nanometers or something. I mean, I'm just amazed that we have gotten this far and continuing to increase the areal density. But in any case, they do fail. So what you can do from a thermal standpoint is do simulations and figure out where do you place the hard drives. We did a nice study back in 2011 where we correlated temperature to hard drive failures, and we did find that it increases exponentially after 40 degrees Celsius. So the idea would be that you want a hard drive case temperature to be less than 40. So that goes into the design as well. The simplest thing you can do is place them in the front. Okay, let's get into the management pieces. So this is, I think, where some of you might find this interesting. So systems management essentially gets into, okay, so I'm a developer, or maybe I'm a system administrator, or maybe I'm a data center technician, and I need to figure out what's wrong with the machine. There's 2 ways to do it. You can do it in-band, which is through the OS, or you can do it out-of-band, which is, if the OS doesn't boot, or you can't get through the in-band path, then you do it out-of-band. So there is a chassis management card for the out-of-band path. And it's basically what it is it's a simple x86 server. So what we do here is we provision this chassis manager card just the same as we would provision a server. So all the automation scripts that are in place for provisioning its server, installing an OS image, making sure that you do patching and whatnot, it all applies here too. So you manage the same thing. You manage it identical to a server. So that's the first thing that simplifies things. The second one is to deal with scale. The out-of-band interface is implemented using a REST API, not using telnet and SSH and some command line scripts that you have to screen scrape. So this has helped a lot by having automation can come in. It's all XML based, and you can manage thousands and thousands of servers all through this REST API. In cases where a human has to go figure out what's wrong, there is a CLI available, so you can essentially go in and start to do serial debug if you want to, although that's not the preferred mechanism. The design was kept very simple. We just used serial. You'll find it surprising, but the connection between the chassis manager and the blade is a serial link, which runs at like 115K baud, which sounds sort of obsolete in this day and age. But the point is, serial connections just work. You don't have to worry about DHCP addresses, and we have found a lot of issues in the past by trying to configure a network within the network. And then you end up with VLAN issues and whatnot. So this was just to keep things very, very simple. Simple and low cost, so it worked out pretty well in that regard. Security, so systems management. Imagine, if somebody gets access to this management network, I mean, they can turn the whole data center off, which is scary. So you want to make sure that there is the adequate amount of security built in. So what we have done here is just typical security policies, defense in depth. So first, the chassis manager card, which is used for out-of-band access, it has a TPM on it, so you can do your secure boot. After you boot it up, then the command interface is through SSL, so your commands are encrypted, and the certificates are set up before that, of course. And finally, you have authentication domain set up. user domains, admin domains that we use through Active Directory. So that way, unauthenticated users cannot get into the machine and do something funny. So this helps us to make sure that our infrastructure is completely secure. The software for all this is, as I mentioned, it's part of that contribution. Talking about the BMC on the server itself. So here, if you look at a classic server, there's a pretty beefy BMC in there. You can do VGA, you can see, the OS booting up, all that, right? So in this case, what we did was, knowing that we want to, keep most of the things automated, we kept the BMC really, really simple. It supports IPMI basic modes. There are very, very few IPMI commands, like, read the event log, turn the server off, tell me the hard drive status, simple things like that. The power control and event logs are pretty much the two things that are done. There is no KVM, no video drivers, no Ethernet, no network stack, no USB, no support for full IPMI. The simplicity is the keyword. So in addition to the out-of-band, so there is a toolkit for operations. So we open sourced this actually just 2 weeks ago. This is an OCS is OCS stands for Open Cloud Server, which is the hardware that I showed you. So the operations toolkit is targeted more for data center operators and system administrators who want to get into the server and figure out what's wrong. It's basically a collection of PowerShell scripts and applications. You can build on top of that and integrate third-party utilities because it's open. We want to kind of build an ecosystem around it. The features essentially are there's diagnostics, there are stress tools, and there are update tools. The diagnostics is to help you to figure out what went wrong. Which DIMM went wrong. What was the serial number of the DIMM. Which location was it in on the motherboard. What hard drive went wrong. Is the BIOS configured correctly? Is it the right version of the BIOS? All those things, right? So those are diagnostics. Well, stress, basically, what that means is once the technician has gone and made the changes to the server, you have to make sure that it is in a stable condition before you can introduce it back to the production environment. So that's where the stress comes in. It runs a whole bunch of disk stress, CPU stress, memory stress, and that will give the technician the confidence that the server is back to normal health, and then they can plug it back into the data center. The final one is updates. This has been a big pain point in the past. If you think about doing like BIOS updates or doing firmware updates, there is this typically a magic sequence for how you do updates. If you do it in the wrong order, you might end up breaking the machine, and you have to follow that certain order. And then a lot of times the technicians are not smart enough, unfortunately, to realize that they don't need to update this one. They should update that piece. So you want to automate this piece as well. So we built this whole set of utilities to make updates as simple as just type a command and say update, and it will go and figure out what is the latest configuration that should be there, what is the configuration that is there, what are the gaps, and then based on what needs to be updated, it will figure out what is the right sequencing and go update it. It's all available on GitHub if you want to take a look at it. Just to give you some examples of the diagnostics piece, so one example here is how do you identify defective components by physical location, a classic thing that a technician want to do before they figure out what to replace. So this command would essentially read the event log, determine the status of this case, the drive, and it will identify where the problem is and point out in a very simple manner to the technician, and go replace DIMM number 5 or go replace drive number 2. So very less chance of errors for them. The next one is an example I'm showing here is a configuration command. So again, if you don't know which machine this is or what it's configured as, you just go there, you type one command, and boom, it spills out the whole information. And in the next case, let me see, I think, yeah, this one. If you want to view specific levels of information, the technician can go and look at all the details of the machine, serial numbers, and so this helps with multiple things. It not only helps with understanding what needs to be replaced on the server during operations, it also helps with doing asset management. because tracking serial numbers and those kind of things, right, have to be done as well. So it's a full set of command suites. Error logs is a big one. Sometimes you end up with a bunch of memory errors, and you don't know whether they are significant enough that you need to replace things or not. So you go read the error logs, and it will tell you whether this is a critical event or not. And depending on the sophistication of the technician, if it's a developer, then they would probably want to look at the raw files. If it's a data center technician, they probably want to look at just high-level information. So you can provide that view of whether it's raw information or whether it's high-level information. And finally, the system updates piece that I mentioned. How do you update the system to the latest version of whatever software needs to be updated, BIOS, firmware, option ROMs, OS images, whatnot. So it's as simple as just say update, and it will go figure out what needs to be updated, what sequence, and just go do it. So that's the operations toolkit. It's as I mentioned, it's on GitHub, available for open download as part of the collateral contribution to the server design that we open sourced earlier. All in all, the designing for the cloud is pretty challenging because the workloads are not only diverse, but they are changing, and the workload changes pretty much every day, to be honest. In some cases, they change multiple times a day. So you have to keep up with how does this workload evolve, and how does the machine that's going to be there for 3 years need to be adaptable to a workload that changes pretty much every day. So it becomes a very tricky problem. And the way to do that is you essentially end up with some flexibility, but some uniformity as well, like I mentioned. When designing for cloud scale, it's not only for servers, even for data centers and networks and whatnot. You've got to design it to be modular, keep it simple, and focus on the operational piece. A lot of times people don't worry about the operations piece, and then it ends up starting to break, and it becomes a support nightmare. And finally, open source server designs, as what you see in the Open Compute, OCP, are a good way to start to build on top of, whether it's the hardware ecosystem or whether it's a software ecosystem, so that others can take advantage of what work you have done. And this is kind of relatively new in the hardware space. Open source software, of course, has been around for a while. Open source hardware has been around for about, I would say, 3 years or so it's still new. So that ecosystem is not as mature, but it's slowly getting there. But what companies like Facebook and Microsoft are doing, though, is making sure that they keep contributing the designs that they use every day in their data centers, so that battle-tested designs are given out, and anybody can use them for any application and benefit from their experience. That's my presentation. I can take some questions if there are any. Okay. Well, here's a mic, maybe. Yeah. I'm sorry, can you speak up?
Might not be on.
Yeah.
Is the management board hot swappable?
I'm sorry, I still can't hear you.
The management board on
Yeah.
the backplane, is that hot swappable?
Hot pluggable?
Yeah, can you replace it without bringing down the whole? Right.
Yeah, so it's hot pluggable in the sense that what happens is, suppose there was some issue and you unplugged it, then the system would default to a safe state. Like the fans would go to max speed and whatnot. And then when you plug the new one in, it will detect that the new one is there, and it will go back to the normal state. Yeah, so you don't have to shut everything off to be able to change it. That's what your question is.
So I was wondering, how much money do you save by open sourcing your servers so that you can actually get competition for it? Or is that a secret?
No, so our volumes are big enough, actually, that whatever economic advantage we can get through volume, we're getting it anyway. Oh. So, so I don't think it being available there is going to move the needle, because the volumes outside won't be as big as what we have. Any other questions? If not, my email address is kvaid@Microsoft. Feel free to send me email if there's any questions I'd follow up. Thanks for coming here, and I'm glad to be here and giving this talk.